studying now, which is about Markov. So you see that, what is my Markov assumption? My Markov assumption just says that, if I am at a particular state today, the chance that I will move to any other state from this state does not matter on how I have arrived at this state. So I was asking if any of you has seen or played the game called Monopoly before. Has any of you played that game, Monopoly? Or sometimes you also have games like, business, where you just roll a dice and you move from one city to the other city and you do business with others. Has any of you heard of that game? No? Yes.
Yes, ma'am.
Yes, ma'am.
Okay. I saw no response. So yeah, okay, fine. So that's good. So what happens in Monopoly is, let's say you start, okay? So once you have kind of started and you roll a dice, you land up on some. So again, you have different kinds of Monopoly, and you have basically have different cities in Monopoly, right? So you'll have, let's say, you can also have the Indian version of Monopoly or the world version of Monopoly, and you'll have states as the cities that you can land upon once you throw the dice. So there are different colors, of course, and let's just for now forget about the colors. We'll just consider the possibility of having those community service. And what's the other thing that you generally have? It's also chance, right? There's one chance and there's another column where you have community service. So if anything happens over there, you might go in jail, or you might land up in the safe house, or you might go back to the start and then again start from the first row, and so on. So there are various other options that the community chance and the chance will offer you. So once you take all of that into consideration, it kind of becomes a bit more difficult. But for now, let's just forget about, those cards. And what we think of is the only cities that you move from one city, let's say, to the other city. So if you roll a die, you'll end up at 5, and you'll move 5 steps forward to, let's say, some city X. Okay, and now if you again roll a die, it again does not matter, right? If you arrive at that particular city X using a 5 or a 1 or a 2 or a 3, what matters is if you roll a die, if it is true, you will move 2 cities forward from X. So that is how the game moves on. And again, there is actually a video on the YouTube, and I will put up a link of it for anyone who is, interested to watch. So there is this mathematician known as Hannah Fry, and I've actually met her. So yeah, she is a mathematician at a University College London, and what she did was, she has a book which is, I guess if I'm not wrong, titled something like The Existence of Santa or something like that. So yeah, it has a nice red cover and it has snowflakes all around the book. And what that book kindly explains and very nicely explains is the Markov model that you can use to basically predict which properties you should buy and which properties you should not. Because again, there is a cost involved whenever you buy a particular property, and there is a return as well, right? Because if another person lands on that property, you get something in return. You get the rent that they will pay, or let's say if you build the hotels in the house, you'll get that as well. So what she does is she uses theoretical model. She does not use any software. She uses she actually calculates each of the sample paths manually and tries to figure out which are the properties that you should eye on buying let's say whenever you're having a decision on to put up a hotel, and let's say you own multiple properties of multiple colors, you will have a guide as to which color you should put a hotel on, so that that color, considering the situation and the community chance and the other scenarios into consideration. So let's say you are more likely to go to jail, right, than any other corner, or you're more likely to come to start, because that is where you can go to if, let's say, you arrive at a chance sometime. So the cities that come after that are much more likely to be visited by other people as well as yourself, and once you go around the board playing. So that's a very good model. And again, the YouTube video that I was talking about, so what happens in that YouTube video is Matt Parker, he's another stand-up comedian mathematician who tries to use Python to actually figure out these probabilities, and he actually kind of arrives at the same kind of probability. So what you'll have is the probability that a particular person will land up in some particular state. So whenever I'm talking about a state, it is a particular city. So again, the chance that you will land up in, let's say, Madras or let's say in Mayfair will highly be dependent sometimes, as you might expect, of where you are starting from. But as we have seen, we look at stationary distributions. So what matters is not where you start from, to see where you will end up in the long run. So that's kind of something that goes behind a very mathematical way to play the Monopoly. But I guess, sometimes you just want to enjoy the game. So you need not get into these details and never try to explain these to other people. They will be like, what's wrong with this guy or something, I guess, until and unless that other guy also studies, I guess, actuarial science or is interested into mathematics. So I guess you guys will be interested. So I'll put up a link of that video where they will actually explain this particular Markov model in detail. You don't need to know whatever we're going to study in this course to know what they're doing there, but just the way you figure out the probabilities and just, what is the meaning of Markov assumption. That's all you need to know. So I guess that's good. You can have a look at that. And again, there are so many magic tricks. So actually the guy who used to teach CT4 before, he and I as well, we are a part of the NGO called DMAT, where we actually teach other people and make you guys, basically make everyone see the beauty side of mathematics. So we don't teach mathematics in the usual way, but in a very intuitive and in a very radicalized way where it's much more fun and not much of work as it kind of seems. So it will involve work in terms of you using your mind to solve, but it won't be like, just work where you're getting bored. So I guess it's good. And he also knows, he knows actually a lot more of card magic tricks, which are based on mathematics. So I'll try to conduct a session of his as well, I guess once when we have all of us, so that it will be much more fun to have a gaming session sort of a thing. But yeah, I guess I can maybe show you guys one trick actually. So I don't know, I think it's been a lot, I guess. Do you guys want to know the magic trick, or do you guys want to continue with the study? I think I can take a vote. What do you guys think? I'll go with whatever you guys say. Do you guys want to see a magic trick which is kind of about stationarity distribution? Or do you guys want to continue with this? So I was thinking on maybe if we can finish the chapter 3 by today itself. And I guess we can actually do that. So what do you guys think? Tell me. Do you guys want to, are you guys tired enough that you guys want a break where I'm just indulging into showing you guys a magic trick? Or do you guys want to study something now and then take a break? And then maybe we can start off the next 2-hour lecture with a magic trick, or maybe end that lecture with a magic trick. Or maybe we can do magic trick in some another lecture. What do you guys think? What are you guys in the mood to do? Are you guys in the mood to study?
Can we continue with the lecture right now?
Okay, all right. So yeah, I guess I'll just continue with the lecture. So no worries. Yeah, okay. So let's just continue with the lecture. And what we studied up until now was something about, trying to figure out a survival probability. So the probability that a life will be alive by age x plus t, given that they are alive by the age x. in terms of the transition intensities that will be given to you. So again, if you see the transition intensities that will be given to you will be, okay, let me just, am I recording? First of all, I should start. I guess, yeah, we are recording. Okay, so what's happening here is we saw that we can summarize this in, oh wait, I haven't written the formula. Let me just write the formula here for our reference. Okay, so what you get at the end is something like this. I don't care. So this is e raised to minus integration from 0 to t mu of x plus s ds. So you see in the formula, what we are actually doing is, we are taking into consideration all the transition rates. So this ds is varying. So this s varies from 0 to 0 to t, right? So basically you'll have mu of x plus 0, x plus 1, x plus 2, x plus t, till x plus t basically, right? And that is what you are caring about when you want to figure out tbx. So I guess that is good. Maybe I should highlight that as well. So this is the final result that you get once you use the separation method and do each of these things. Okay, so now what we are going to do is, you kind of want to figure out this mu, right? Now we know, if we know the mu, which is the transition rate, I can easily figure out my transition probability. But how do I figure out my transition rate in the first place? Because even that is not given to me always. Okay, so let me just construct a theoretical model where I will assume that I know certain things and I do not know certain things. So we'll try to derive this mu using what we know. So even before we do that, I'll have to define again the scenario that we are looking at now. So let us say that I'm conducting an experiment. So where I'm looking at observations. So when I'm talking about observation, it means the policyholders that I'm looking at. Okay, so what I will have here is, let's say, let me just draw a line. So if I draw a line here, what I have is x plus ai. So let's say this is x and this is x plus 1. So I'm again looking at in between the 1 year period, let's say, if I'm defining my x as age. So I know that x plus 1 and x, so the difference between x plus 1 and x is exactly going to be one particular year. So I define x plus ai, where this ai can again be any number between 0 and 1, which denotes the entry point. So when I'm talking about entry point, it is the time at which I start observing a particular policy holder. So from now on, I'm just going to call that policy holder alive. So this is the time where I start my observation of the ith life. And again, I just define x plus bi, which is where I define the exit. So let us say I'm conducting an experiment from this time to this time. And again, I know that any of these people can actually die in between, or they may not die as well. So this is the theoretical and the scenario that we're looking at for now. So again, let's just say that I have in total capital N number of lives that I'm looking at, and all of these are identical and statistically independent. So these are IID, and I mean, yeah, it's fine if I put a D as well, I guess. So, okay. So now what I'm seeing is that I'm observing lives. So again, here I'm defining my lives as I. So what I can say is that I'm observing N number of lives. So I can go from 1 to my capital N. But again, what I'm doing is, I'm saying that if let's just start my experiment for all the lives that I have, when they are aged 80.25. So let us say this is 80, then this will be 81. So let us say this is 80.25, and let's say observe them for 6 months. So this will be something like 80.75, right? There are 6 months that will be covered, and that is my time of observation. So sometimes what can happen is, let's say you start observing one particular life, which is, let's say, life second, and that particular person dies even before your observation ends. So what's gonna happen is, you might know what to do, right? Because sometimes you think that all of this information is necessary, but again, what will actually help you is to know the number of people who have actually died within this. And again, once you reach this point, let's say you have reached 80.75, then you don't know that after 6 months, whether the person is dead or whatever happens to that person, it doesn't concern your model, right? So that is called right censoring, where you only know something up until now, and then after that, you do not basically know what's going to happen to that life. And again, we don't care to know because this is my observation time period. Okay, which is kind of like 6 months for this particular example that I was trying to give you guys. Okay, so I guess once we have that, now this is known as type 1 censoring. So there can be two different types of censoring and many more as well. And we'll have a look at the types of censoring as well in depth in upcoming chapters. So whenever I say that, I've already predetermined the time when I will stop my observations of my policyholders or of my lives. That is time one, that is type 1 censoring. And let's say if I say that, I want to stop my observation up until, so I'll only stop my observation when I have observed 4 deaths among these N people. So that kind of a censoring will be type 2 censoring, wherein your experiment stops whenever you have, a predetermined number of observations that you expect to be dead. So that will be type 2 censoring. But again, here we are doing type 1 censoring because we have predefined our time of observation, which is 6 months. And it doesn't matter how many people die here. We are going to stop our observation at 80.75. So this is the construct of our model. And again, now if I'm talking about this X plus BI, if we were looking at the type 2 kind of censoring, this BI wouldn't be known to us, right, from before. So what you will have is this BI will be a random variable. But now that you have already defined this as 80.75, know that your BI is just 0.75. So in type 1 censoring, you sort of know the value of BI. So it is not a variable anymore. It is just some another constant. Okay, so I hope that's clear. And now if I have to analyze, so you see the only information that I as insurance company will have is the observation time period, or maybe if let's say someone dies in between, so you'll only have this much of time. So the best thing, the appropriate thing to say will be, the time spent under observation by a particular life. So you will know that information and you will only know the other information, which is if a person has died or not. So let me use a random variable di here. So I'm going to use a random variable di here, which is an indicator function, and it takes a value 1 if the ith life is observed to die, and it takes a value 0 if ith life doesn't die. So again, we are talking about this life being dead or this life being not dead only with respect to the observation time period. We can't possibly say anything about what happens after the observation time period ends. So that you should always take into consideration. So this is just the random variable which will give us information about whether a life has died or not during the time we were observing that one particular life. Okay, so once we have that, now we also will, you can just easily see that if you add up all these DIs, what you will get is the number of deaths that you have observed, right? But again, now if you want to figure out, let's say the expected number of deaths, so the expected number of people you expect to die. Okay, so that will be expectation of PI. What will this be? This will just be, the probability that you observe PI as 1 times 1 plus the probability that you observe BI as 0 times 0. So this is just going to be 0, does not matter at all. So you see that the expected number of deaths that you observe is actually equal to the probability that a life will die. So again, what is expectation? Expectation is just what happens on an average, right? So it's addition and then dividing it by number of observation. So what it boils down to is just the probability that a particular life will be dead. So again, what do we know about the probability that a particular life will be dead within the observation time period that I'm having here? So I can just rewrite this in terms of the TQX formula that I've studied. So now can anyone tell me what should come here and what should come here? And remember, I want to figure out this probability, and what I also, maybe I should just highlight it again. Okay, yeah, so I guess I want to figure out this stuff, and I'm using that this is my entry point and this is my exit point. So can you tell me what should I write on the right hand side and what should I be writing on the left hand side? Anyone? What do you guys think?
Ma'am, will it be on right hand side, it will be x plus AI, and on left hand side, it will be BI minus AI.
Exactly right. And why do you think on the left side, Savi, will it be BI minus AI?
Ma'am, because like we are looking till x plus BI. So if we add up left hand side and right hand side, we get x plus BI, and that is what we are looking for.
What did you say? If we add up the
no, like
okay, yeah, exactly right. So again, I mean, what she is trying to say, in other words, you're exactly correct, Savi. Thank you very much. So what we are going to do is, here we write when we start our observation, right? So we are starting our observation at x plus AI. So given that the person is alive at x plus AI, what is the chance that the person will be dead by the time we reach x plus BI, right? So again, whatever comes here is just the increment. So to derive this particular thing, what you will do is x plus BI minus x plus AI, right? And that will give you BI minus AI. That's it. So I hope this is clear. And this is kind of intuitive as well, I would say, that the expected number of lives that you observe to die is just equal to the probability that you will observe a life to be dead. Okay, so now this is clear, but this is not gonna still help us, right? So, okay, let's just, so what we're gonna do is, sometimes okay, so now we have thought about what happens to the number of people who died and the number of lives that we observe to be dead. But we also have to care not about the total time period, but about the time that these people spend under observation, right? So to figure out the time that these people spend under observation, let's just define another random variable. So what I'm going to do is I'm going to define a random variable ti such that my x plus ti. So again, this ti will be between 0 and 1, of course. And the maximum value that this ti can take is bi. And the minimum value that this ti can take is ai, right? So I'm just going to define that x plus ti is the age at which the observation of a life, I've written I ends. So sometimes if let's say a person dies in between, the TI will be less than B, right? The less than BI, right? Because BI is the end limit. And let's say if the person does not die at all, then you know that your TI is just going to be equal to BI. So you can clearly see that these variables DI and TI are not independent. So what you can see is that if your DI is 0, which is that there is no death that is observed, then you know for sure that your TI will just be equal to BI, right? And let's say if you observe a death, then what will happen? You cannot pin down TI, but for sure you will know that it is going to be greater than AI and less than BI, right? It cannot be equal to BI. It will be in between these. Here, anywhere, it could still be here. So the only condition that we have is that it should be less than BI and greater than AI. So these are two values that your TI will take depending on your DI. But again, you can say that these aren't the two values that TI takes. So these are like two kinds of values that your TI can take, because here it's taking one particular value, which is BI, but here TI can be anything in between AI and BI. So the number of values that you will observe for TI are the number of I's that you observe, which is capital N in this case. So, okay, if that's done, now if you have to figure out what is the time that a particular life spends under observation. So again, x plus ti is the age. So remember when I was defining x plus ti, it doesn't represent a time. It represents a particular age of my observed life. Okay, but again, instead of age, what I find more useful to work is the time that a particular life is going to spend being observed. So what I will do is I will define another random variable. I know I'm defining like so many random variables, but trust me, I think once you fit the model that you're looking at, it will be very easier for you to even see these things. But let's just say VI is another random variable that I'm defining, which I say is the time spent under observation. Okay, so now can you tell me, using this age and this model that we're looking at, how can I rewrite the time that life will spend under observation? So again, remember this x plus ti is just, it can take any value here. So what will be my VI? So I'm not talking about the total time that all of these lives spent, but I'm just talking about one particular life because I have V subscript I. So that I is for one particular life. So how do you guys think I can rewrite my VI, which is the time that is spent under observation, using this and the thing that I have just defined now? Any one of you?
So we want the time with respect to ti, right? Ti random variable.
Yeah.
So x plus ti minus x plus ai.
Exactly right. So that is what you will do, because we know that TI is just a generalized version, because not every time you will observe BI. You can die, the policyholder can basically die anywhere in between these So we have generalized that in terms of TI. So this has certainly helped us to figure out the time spent under observation. So now I can rewrite my VI as X plus TI, which is the age at which the observation ends, minus the age at which the observation starts. So what does this give me? It just gives me TI minus AI, and this is my VI. And the another way you can actually interpret this is actually waiting time. So this kind of Markov models are heavily applicable in queuing processes. So whenever I'm talking about queuing processes, these are like the processes, let's say, if you are a restaurant company and you want to see how much a customer has to wait before they get their order. So that will be your waiting time, right? And that waiting time is the period they are under observation. So it's like the time where they are in the line and they haven't yet reached the counter. So it can be that as well. So it's like the time it takes for them to reach a particular counter. And that is why they're waiting over there, to reach a particular counter. And that is the time that they are spending under observation. So our end goal, which I say here, is that in the restaurant example, it will be basically ordering the food that they want to order. So that will be the end goal. And the waiting time, the observation period will be when they're waiting in a line. So that is how this PI also has another name, which is sometimes known as waiting time. So VI can also be slash known as waiting time. So again, if you now see what will happen with VI is that what is VI? It's just TI minus AI, right? So now depending on the values that your TI will have, so depending on the values of your TI, your VI will change, agree? And now you know that your TI depends on the values that your DI takes, right? So you know that all of these are kind of interlinked with one another. So there is certain connection between DI and TI. And I know that my waiting time is also connected to TI. So I know that my VI and DI are in a way connected. So for any particular life that you will be observing, so for any particular sample that you will have information for that one particular life about if they are dead or not, or how much time they have spent under the observation, right? And if they're dead, it will be like less than BI minus AI, or if they do not die, then it will exactly be BI minus AI. So whenever I say that it can be less than BI minus AI, it can be anything, right? So it can be 0. Let's say if you're starting at, just take this example. So your TI could be anywhere in between. So your TI minus AI basically could be anything from 0 to 0.5. And this will be your value of VI that it can take. And at the end, your VI can be sometimes precisely 0.5, right? Which is what happens when the life does not die. So you know that you will sometimes have this continuity, and sometimes you just have this probability mass for VI. So let's say if I were to plot my VI, I can observe something like this, and then I'll just observe a mass point over there. So we know that VI is neither a continuous nor just a discrete. It is a mixed distribution where it has continuous as well as discrete observations. So I guess that was it. But now let's just try to figure out the distribution of this VI. So I know that my VI depends indirectly on my DI. So it does not quite make sense to only figure out the marginal distribution of VI. So what we are going to do instead is figure out a joint distribution for DI and VI, which is one particular pair. So what I'm going to say is that for each life, I observe a pair, which is DI, VI. So what I'm going to do is, now I will try to figure out what are the chances that I will observe some particular DI and some particular VI. So you will only know, the value of DI and the value of VI from the information that will be given to you. So maybe I can actually, even before we do the derivation, just to give you guys a glimpse of how it looks like. I can give you guys some idea. Yeah. So if you can see this table, what it has is, it has the date of birth of the people that you are trying to observe. It has the date of entry into observation, which is basically the date you started to observe each of these particular people. And then you have date of exit from the observation. And then here you have the data whether they have died or not. Okay, and this is again in between these periods. So you will know, so again, they are saying that, the force of mortality between the exact ages 70 and 71 is assumed to be constant. And again, whenever they are saying 70 and 71, you would obviously know that each of these lives is being observed from 70 to 71. So again, for these people, you see it is precisely one, right? 1 Jan 2017 to 1 January 2018. But now if you see here, it started at 1 March 2017 and it ended at 1 September 2017. So you see that this particular person died actually on 1 September 2017. And that is why you didn't observe that particular life after this period. Otherwise, for rest of these guys, again, there might be some particular reason. So if you see here, there is again a discrepancy. You started at 1 June, you ended at 1 September, but again, there is no death here. So there might be other reasons as well. Maybe the person was no longer interested in being observed. So that can be one of the reasons. And again, there can be basically other reasons. So yeah, basically for now, what we will take into consideration is the death and the no death scenario. And then again, you see that VI, which is the time spent under observation, will change for each particular life. And that is what you know. But again, what we want to figure out is the transition rate. And how can we figure out the transition rate? That is the question. But even before we do that, we will try to further analyze the VI and the DI variable that we have now. So going back, I guess, to trying to derive the distribution function. So this is the kind of thing that you will be given, right? This is what you will know, and then you'll have to kind of analyze. So here they're saying you to, estimate the force of mortality mu using this particular data set and blah, blah, blah. So we'll just study that now. Okay. So now that I know what I have here is, for each life I've observed a particular pair, DI and VI. My DI is the number of deaths and my VI is the time spent under the observation. And these both in a pair pertain to a particular life that is being observed. Okay, so now that's clear. If I want to figure out my function, so this is really not going to be difficult, right? So whenever I'm talking about a density function, what do I know? I know that a density function is just trying to figure out the probability of observing something, right? So what we're going to do is to figure out f of vi comma di. So again, remember, whenever I write capital Di, I should be consistent. So whenever I write capital Vi and capital Di, what I will have here is a random variable. And these are the observed values of this particular random variable. So you need to be mindful of the capital and small notations that we also use. Okay, so now we want to figure out what is the chance, like what are the possibilities that you can have for this particular function. So I know that I can either, so this is observation for one particular life, I, right? So that life can either not die or the life can either die. These are the only two possible scenarios that I can have for one particular life, right? So now the chance that I will observe this particular life to be, not dead. So I can represent that as the probability that my life was alive when I started the observation and it is alive till the end. So this is what you will have, BI minus AI. And that doesn't look like AI, I guess. So yeah, BI minus AI, which is just X plus BI minus X plus AI, which is the whole time period when you have observed them. Okay, but now let's say if a person dies, how will you figure out the probability for that one particular person? So what you know is the time spent under the observation is VI, right? So you know that the person was alive up until VI and then instantaneously that person died. So what you will do is you will have the probability that you started observing that life at X plus AI and this much was the time that particular life spent under observation. So this is the probability that the life was alive at X plus AI and the life is still alive at X plus AI plus VI. But now you know that the person dies, right? So you will multiply this with the transition rate, which is mu. And again, what will the time be? It will just be X plus AI plus VI, right? Because that is when you expect this particular life to die. Does this make sense? Any doubts in this particular denotation of this density of DI and VI? Any doubts so far? No doubts? Okay, so now what I have done is just, the basic thing is that there can be two things that can happen with the life that we're observing. Either it can die or either it will not die. So we're just trying to figure out the likelihood of, them dying and likelihood of them not dying. So these are the particular probabilities that you will observe. But again, now we also know that, we can rewrite these p's in terms of u's. So let's just try to do that so that we have an equation which is everything in terms of u's. So again, I'm just rewriting this thing. So I know that I can rewrite this using the formula that we just derived. It will be e raised to minus, it was from 0 to t, right? So here I'll have from 0 to bi minus ai. And what I will have is mu of x plus ai. And again, I should not be forgetting the dt part that I have. So it will be plus t dt. Okay, and this is again for the case where I observe di as 0. So let me just go back, I guess, once. So if you see, the thing here was tpx, the probability that if the person is alive at x, the probability that he will still be alive at x plus t is e raised to minus 0 to t. This t comes from here, and then you have mu of x plus s, which is something that you take the derivative with respect to for a placeholder for this particular random variable here. So the same thing you do here, and this is what you get for di equal to 0. But now for the case of di equal to 1, you have this. So this will just be again e raised to minus integration of 0 to vi, okay, mu of x plus ai plus vi. Okay, so you can't have vi here, right? You see what you will have is the placeholder for vi here. And that is what? That is just the t here. So this will be t dt. And that will be your writing for this particular guy, and then this will be multiplied by again mu of x plus ai plus vi, which is as it is. And this is the case when you observe di is equal to 1. So does this make sense? So maybe I should just do a bit something like this, that these limits are for this particular people. Yeah. And again, so this thing that you observe can be written as this thing. So I hope this is clear for everyone. Any doubts so far? So what do you guys observe here? There is something going on, right? So I know that whenever my di is 0, what is the value for my vi here? Whenever my di is 0, the value for my vi is just ti minus ai as it is. I mean, and whenever my di is 0, my ti is bi. So my vi is just bi minus ai. So if I were to rewrite both these equations in terms of one particular general equation, I can actually rewrite this thing as e raised to integration of minus 0 to vi. Because again, I'm not differentiating in between whether it takes a value 0 or 1. Because I know that if it is 1, it's going to be vi. And if it's 0, it has to be bi minus ai, which is what the value of my vi will be if my di is 0. So I don't care much because that's not going to change. And I'll have this as it is, right? Because this is the same. So this is mu of x plus ai plus t dt. Okay. So once you have this, this will be multiplied by what? So now you see that there is no ui here, but there is a u something here. So you see that you will write mu x plus ai plus vi. And now because you're defining di equal to 0 and di equal to 1 as the indicator function, you can actually just raise this thing to the power of di. So that if you have di equal to 0, you will get a value of 1. Because this will be raised to 0. So that will just be 1 and you will get this equation as it is. And if you have di equal to 1, this will be 1 and basically you can remove that and you will end up with this, which is precisely what you have here. Does this make sense to you guys? So again, any doubts? Yeah?
No, ma'am.
Okay, thank you very much. So now we have kind of used the Markov assumption, yes. We have also, so now what we can do is actually, we can use the assumption tree to simplify this. This mu of x plus blah, 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 this looks a bit complicated. So what we can do is, we can simplify this. So what we do is, let's just assume that mu is constant. And observation time period. We don't care about what happens to mu when we are not basically taking it into account. But yeah. Okay, so I guess so this is not general f, this is my particular f for a particular life, right? This is my fi. So now what I'm going to do is, I can actually say that my fi di comma vi will be what? So we'll go back and forth and we'll see what we derived. So it was e raised to minus mu dt and then this thing, right? So now we won't anymore have to write these subscripts. So you see what we will end up is, with is, it will be e raised to minus integration from 0 to vi. This will still remain vi, and you'll have mu here and just dt here. So no subscripts to mu because it's kind of same everywhere. And this will be mu raised to di. So this is what you observe. But again, now you know that because it's just a constant and there's no t here, you can actually solve this integral, and what you will get is something like mu t, where your t is taking values from this to that. And yeah, so you get e raised to minus mu vi and mu raised to di. And this is your fi di comma vi, which is the joint density of fi of di and vi basically. So you see it is, so now you see why do we have to take t as a placeholder for the waiting time here, because at the end you want these to be function of vi and di. So that is how you arrive at the likelihood that you will observe a particular pair of di and a particular pair of vi. So again, this is just for one particular life. But what we want to concern ourselves with is not only one life, right? We observe so many different lives. But the one assumption that we made in the start was that all of these lives are kind of identical and independent of each other, right? So now to figure out the joint probability function of each of these lives, what we will do is we will, so for all the lives, the joint probability distribution will be something like the multiplication from 1 to n, where you are just multiplying this f of i's, right? Does this make sense? So again, now I will just substitute for this guy where I goes from 1 to n, and e raised to minus mu vi, mu raised to di. So now what you can do is, because these are in raised to e raised to, so you know that what you can do is you can just add it up across in its numerator. But again, you know that you observe mu raised to di. So let me just maybe. So can you guys see that? Maybe let me just write it. E raised to minus mu, let's say v1 times mu raised to d1. Then it will be e raised to minus mu v2 times e mu raised to d2, and so on and so forth, till e raised to minus mu vn, mu raised to dn. So you also have e raised to these stuff, and you also have mu raised to d1 times mu raised to d2, and so on till mu raised to dn. So you can summarize this, all of these stuff, as e raised to minus of mu of addition of all of these vi's, right? So v1 plus v2 and so on till v capital N. And here what you'll have is mu raised to addition of all the di's. So d1 plus d2 and so on up until dn. Does this make sense? So now what you see is these powers that you have in terms of addition. So the example that I just showed you, this would be 2, right? Because there were only 2 deaths out of the 8 lives that we observed. So what is this? This is just the number of total deaths that you observe. And this is the number of total waiting time for each of the lives that you observe. So this will just be basically, let me take you guys back to this case. So here your D1 is 0, D2 is 0, D3 is 1, D4 is 1, and rest of them are also 0. So you'll have mu raised to 2. And here what you will do is you will have to subtract. So you'll have to figure out the number of months that there are and divide them by 12 and add all of these up to get your total VI. So basically VI for this guy would be, let's say, just 1. So, and so on and so forth. So does this make sense? So that is how at the end you will figure these things out. But again, I mean, just to be a bit precise, what you can also do is you can just use, I mean, you can just denote small d and small v. So maybe just let me rewrite this thing. So basically what you will be doing is this will be e raised to minus mu of just some small v, and you'll have mu raised to just some small d, where I'm saying that this v is these additions and this particular d here is these additions. So I can also actually just rewrite where my v is summation over vi's, where I takes values from 1 to n, and my small d is summation over di's, where I take values from 1 to n. So remember, in the previous case, what I defined was some bi and some vi, which was the death observed for a particular life, so 0 or 1, and this was the waiting time for one particular life. So now what we have done is, we have just derived the aggregates. This is the dates for all of the particular lives, the number of deaths that we have observed, and this is the waiting time for all of the particular lives. So this is kind of intuitive, I would say. So what we have here at the end as the formula is something like this. So this is e raised to minus mu v times mu raised to d. So what you can do again is define this. So this is the value of the waiting time and this is the value of the number of deaths. So again, these are the values that these take. So whenever I'm defining, I can maybe write, f of d comma v. So this will be corresponding to the value taken by the random variable capital D, and this is corresponding to the value taken by the capital random variable V, where this is the total deaths. This is basically the total number of deaths, and this is basically the total waiting time, not number. This is just the total waiting time. Any doubts so far? Anyone? Okay, so I hope this is pretty clear, and let's just take a 20 minutes, let's just take a 30 minutes break, and we'll meet again at 5:10. Is that all right? So there is actually a sum related to just what we have studied right now. So do you guys want to do that sum and then maybe start by 5:30, or do you guys want to do a sum later on? Depending on what do you, I'm recording here. Good. What do you guys say?
Ma'am, after the sum, how much more time do we need?
How much more time? So I'll just need a 2-hour class. I'm not going to take much more than that. I mean, we'll finish the chapter number 3 by today. It's really not much. I mean, not much is left. The tough part of the chapter number 3 we have already covered up until now. It was just, this derivation, and there are some derivations again in the upcoming part, but you do not need to know that. So I'll just walk you guys through over that derivation, but yeah, you won't necessarily have to prove that anytime. So it's not going to be that difficult. So I'll just take 1 2-hour class from whatever you guys decide. So if we do the sum now, okay, I think let's just do the sum now, if you guys are in the mood. So let me take you guys back here. here. Number one. Okay, so this is the sum. Can you guys see? Okay, so it says that, we are observing a particular life and we are beginning its observation at the exact age 82 years and 3 months. So who would like to convert this into the decimal that we just studied about? So when exactly are we starting observing the life? What is my AI here basically? What will be my AI? Let's say if my X is 82. So if we're starting at 82, 83. So there will be some point where we're starting the observation and some point where we're ending the observation, right? So, okay, they're saying that either the 83rd birthday or death. So, okay, we are going to go up until there. So what do you think I should write here? What is the age? It will be 82 point. So we have 3 months ahead of 82, right?
2.
2-5. Did you say 2-5, Saudi?
Yes, ma'am.
Yeah, exactly right. It will be 2-5 because so to determine what will come here is just 3 upon 12, which is 1 upon 4, 0.25. So you add that up to 82 and you get 82.25. So that is when you are starting the observation of this particular life. Okay, that's good. And they are saying that you continue until the earlier of the life's 83rd birthday or death. So you know that this is all the time that you are taking into consideration. And again, if the particular person dies in between, so then that would be the waiting time that you will have. Okay, so again, up until now, we haven't yet studied how do we figure out the actual formula for this mu guy. So they have given us, assume that your mu is 0.1. So let's say if you are in the alive state, there is 10% rate. So there is like 10% rate that you will move to, that you will die basically. So let's say there are 100 people. At each instance, 10 people are dying. So that's what's happening. And then now they're asking us to determine the probability function of DI. So this is, remember, this is not VI or DI together. This is just the probability function for DI. So again, what do you mean by probability function? Basically, we are trying to look at something like this, right? So DI will take with some probability, and I know that my DI can either be just 0 or my DI can either be just 1. So have we derived this? Do we know the probability that you will observe a DI as 0 and the probability that you will observe a DI as 1? I think we have, right? So what do you guys think? So let me maybe just go back to what we studied. So if you have a look precisely here, we know the probability that your DI will be 1 is something like this, right? Probability that you will die is when you're starting and then Q and then when you're ending. So that is what you're going to do here as well. Oh, it's gone. Okay, fine. So maybe I'll just write again. Okay, so now if I want to figure out the probability that my DI will be 1 and the probability that my DI will be 0, what will I be looking at? So the probability that my DI will be 0 and the probability that my DI will be 1. What do you guys think? So I want this in terms of P and in terms of Q, right? So if I were to write the probability that my DI will be 1, what will this be? In terms of Q. And again, if I'm talking about the probability that my DI is 0, I know I'm saying in a way that there was no date observed. So I've observed the life throughout the time period I was supposed to observe. So this is easier to do, right? I can just write P, and this is the time when I started observing that particular life, which was 82.25. And again, I went on till their 83rd birthday, right? So there is 0.75 difference. 83 minus 82.25 is 0.75. So this is the probability that you will observe no death. So now, how can you rewrite the probability that you will observe a death? Anyone? In terms of Q or in terms of anything else? What do you think?
And you can directly write it as 1 minus 0.75 P 82.25, right?
You can actually do that, right? Because you won't know when this particular person is dying. So you won't know when, like, till when are you observing this particular guy. So it's going to be very difficult to rewrite this in terms of Q. So what you can just do is, you know that if life does not die, then, sorry, if life dies, then it will just be, 1 minus the probability that you will observe a life to not be dead. Okay. But we do know how to figure out this as well, right? So to figure out P 82.75, 0.75, what you can do is we can maybe go back to again what we derived. We derived this, right? And again, now we're assuming that mu is just constant. So I remember deriving this formula when mu is constant is null. I guess I haven't done that here. No. So, okay, if this mu is just constant, what do you guys think this will be like?
E raised to minus mu t.
Right, exactly. This will just be e raised to minus mu t. So that is what we're going to use now to figure out the value of the TPX that we have. Yeah. It's again gone. Okay, so I keep forgetting that it keeps going off and on. But I remember what we had was E 82.25 and 0.75, right? For the probability that you observe your DI as 0. So to figure this thing out, what will you have? I remember the formula was e raised to minus mu t, right, Mihir? And what you will have here is minus mu is given to you as 0.1. And what is your t? T is this 0.75. So that will be whatever you get here will be your probability that you observe DI as 0, and 1 minus that will be the exact probability that you will observe DI as 1. So then they're also asking you to figure out the expectation of DI, which is going to be pretty easy. And just the probability that your DI is 1, because 0 times the probability that DI is 0 is always going to be 0. And the other value that DI can take is just 1. So this probability will be the expected value of DI as well. Yeah. Any doubts so far? Anyone? Okay. So the next thing that they're trying to ask us now, this was kind of, I would say once you just get hang of, these notations, this becomes fairly straightforward, but not that straightforward as well, I agree. Okay, so moving on, what we have here is the probability density or mass function of VI. Okay, so now if I want to figure out the PDF for my guy VI, what I'll have is, let's say, f of vi again. I want to figure these things out for all the values that my vi can take. So can someone tell me what are the values that my vi guy can take? So what are the values that my vi can take? Anyone? What will I have? Yeah. So what are the values that my vi can have?
It will be from 0 to 0.75, right?
It will be from 0 to 0.75. Yes. So again, I know that, it can either be just 0.75, which will be the case if my guy does not die, right? And if that particular person dies, it will take value in between 0 and 0.75. So it will just be less than 0.5. Is this enough? This takes into account the discrete case as well as the continuous case, right? So again, now what are the chances that I will observe these particular VIs? Anyone? So the easiest I would say is to figure out this guy, right? What is the chance that the person will not at all die? And we have already figured this out. So this will just be P of 82.25 and 0.75. But what about this? What do you think will happen here now? So let me take you guys back to when we did something similar here. Yeah. So something from this page is going to help you guys to figure out what you will have to do now. Again, keep forgetting that it's gone. Yeah, so yeah, so what do you guys think will happen here? So again, I do not know precisely what my value for VI will be, right? It can be 0.7, it can be 0.71, it can be 0.711, it can be 0.7111 as well. You never know what it's gonna take. So it takes continuum values. So how can you rewrite this thing? So remember, I'm saying that I have observed, I could only observe the life for VI time, and then that particular person died. So basically I'm saying that up until X plus VI, I have observed this particular guy, X plus AI plus VI, and then this particular person died. So how do you guys think I can rewrite this in terms of the probabilities? Anyone?
And we have written the expression for constant mu, right? E raised to minus mu vi into mu raised to di. So we can use that here.
E raised to?
E raised to minus mu into vi.
Yeah.
Into mu raised to di. So we can use that here, right?
What was that form here?
Mu constant, right? So we have here mu as constant.
No. But what was that formula for? Was it only for VI or was it for DI, VI together?
It was for joint distribution.
It was for joint distribution, right? So very good, very good. We have to be careful about this as well. You can't put a joint distribution here in the margin. So, forget about these formulas and everything. If you want to figure out the probability that you will observe a particular person who is alive up until x plus ai plus vi, and then that person dies suddenly, how will you write that as?
So the person is alive till VI, right? And it dies instantaneously.
Yes.
So the starting age is 82.5. So and it survives till 0.75, right? First.
Yes.
So 0.75 P 82.25, and then mu 82.25 plus 0.7.
Okay, so what does this say? This says that I started observing the particular life.
So here
at
VI should be there in place of 0.7.
In place of this should be VI, right?
Yes.
So what I can essentially do is I can just rewrite this as VI P 82.25 times mu. Let me erase this thing and this stuff. So the probability that I observe this person alive up until 82.25 plus VI, and then this person dies suddenly. So this will be just 82.25 plus VI, right? And this is what happens when VI is less than 0.75. Okay, so maybe what we can do is we can figure out these probabilities as well. So I know that this is going to be same from what I have derived earlier. So just 0. I'm just going to write this. This we already derived. But now we want to derive this guy here. So again, we are being told that my mu is just constant throughout. So it doesn't matter whatever you have here. Your mu is just going to be 0.1. And again, you can figure this thing out. So this will just be e raised to minus mu. And what is my t? Vi. So this is your distribution for the Vi function. So that will be your answer for the part 3 of this particular question. And then for part 4, you will again just have to take its expectation. So the only difference with the expectation that you took with respect to DI and the expectation that you will be taking now is that for DI, you had two discrete values, right? So it was a proper discrete distribution. But now for VI, you observe there is one part which is continuous and one part which is discrete. So what you will do is you will take integration from 0 to 0.75, and you will integrate this VI. Because, I mean, this makes intuitive sense, right? Either the person will not die and VI will just be 0.75. In that case, you multiply it with the probability that this guy will not die. And then you know that this VI can vary in between 0 and 7.5 in continuum numbers. So you will just multiply that with the probability that you observe this guy here. So again, whenever you are taking expectation of VI, you need to consider, I mean, let me just go and write it. So if I'm figuring out expectation of x, what do? I take x times f of x dx, right? So here, if I'm going to figure out expectation of vi, you have to multiply with a t here and a dt here. So this t here is a placeholder. So this is actually a placeholder for waiting time. And this is what you are changing, right? So this is what you are changing from 0 to 0.75. That is why you take integration from 0 to 0.75, which is the waiting time. And here instead of VI, in place of VI, you are just using T as a placeholder. So what you will have is T times 0.1 e raised to minus 0.1 T dt. You can also write VI. I mean, it wouldn't make much difference, but it's just that you will have to write VI, then TVI. I mean, it's fine if you do that as well. Not much of difference it's gonna make. Is that clear? And then again, I guess you can just differentiate. Sorry, you'll have to just, integrate this stuff. So to integrate this, you will have to use integration by parts. So again, this will be, So because you have t times 0.1 e raised to minus 0.1 t. So you'll have to use the same formula that we just saw, and you can figure out this differentiation, this integration using integration by parts, and this is just as it is. So you'll get to your final answer for the expectation of VI. Any doubts so far? Any doubts?
No, ma'am.
What about others? Savri and Vanshita?
No, ma'am, it's clear.
Okay, Vanshita?
Yes, ma'am.
I'm not sure how much of this are you getting, Vanshita, but I guess
Actually, not 100%, but I'm just trying to.
yeah,
I
it's
have to watch this lecture again as well, but yeah.
yeah. But now you can watch it at twice the speed, so I guess that will be fine. But yeah, I guess that's it for now. We'll take a break. Oh, how much of a break do you guys want? I don't mind. Let me just stop recording now.